about what is a system on chip. So if you were not there for the previous session, I'd like to cover a few details about what we discussed there. So I talked about what is a system on chip in the previous session. So literally, system on chips are at the heart of computing devices, from simple IoT devices and smart homes to complex navigational systems in airplanes. So system on chips are in contrast to a common traditional motherboard-based PC architecture, which separates components based on functions and connects them through central interfacing circuit boards. Whereas a motherboard houses and connects detachable or replaceable components, a system on chip integrates all of these components into one single integrated circuit as if the functions were built into the motherboard itself. So as you can see in the images, in the Raspberry Pi first generation, the Broadcom BCM2835 system on chip was used there. So it included a 70 megahertz ARM processor, a video graphics processing unit, and a random access memory. And I believe that you are familiar with Apple chip. So this is Apple A12 Bionic chip, which includes a 4-core GPU and a 6-core CPU, and also some accelerators inside. So I believe now you have a certain idea about what is a system on chip is. And so when I go into the definition of a system on chip combines the required electronic circuits of various computer components onto one single integrated chip. So as you can see in the image, within a one single silicon die, you can find a GPU, you can find a CPU, a memory, connectivity modules, DSPs, and any other component there. Yeah. So in the modern system on chip designs, there are like several sensitive assets. Some are like encryption keys, device configurations, onboard protected data, and that are responsible for keeping our personal, financial, intimate, physiological information safe and secure. So this illustrates what the system on chip is, and you can have an idea about what it is, because in this example, you see a system on chip with network on chip based communication fabric to interact with a wide variety of third-party intellectual property codes. So giving an idea about what an intellectual property core, this is also discussed in the previous session. So an intellectual property core in semiconductors is a reusable unit of logic or functionality or cell or layout design that is normally developed with the idea of licensing to multiple vendors for using as a building block in different chip designs. So if you did not understood what it meant in this sentence, so these GPUs, CPUs, memories, others, DSPs are intellectual property cores, and due to the complexity of the design of the system on chip, some of these cores are designed by other vendors other than the one who is designing the entire system on chip. So there can be some security issues because the other vendors might not be might have some malware inside those system on chip designs as well. So basically IP core is a part of the system on chip that you can see as a GPU, CPU, memory. Yeah. So about how IP cores communicating. About how IP cores are communicating, there are like 4 things that we have to discuss. One is the topology, the other one is routing, flow control, and architecture. Topology means the connections that are there, and routing is the path that we are going to use it, and flow control is about the rate of data transmission, and architecture is how the routers are built. So consider a designer who is responsible for designing a road network of a large city. So when it is done, the road should be laid out to giving access to all the offices, houses, schools, parks, and etc. So if all of these most common places are situated close to each other, it is inevitable that the roads in the connected area will get congested and the other area might be relatively empty. So when constructing a road network, one thing is like, let's take this example where it connects multiple cities through different paths, and when multiple cities are connected via paths, we can find different paths connecting those cities. So that's an option as well. So as well, when there's a path, there can be like uh, traffic traffic lights, and some paths might get congested because of the traffic. So traffic management is required, and then there are like multiple lanes in the roads. So there should be accessibility as well. So the designer should make sure that such instances do not occur and the traffic is uniformly distributed as much as possible. Alternatively, the road should have more lanes and parking lots such as congested areas to cater the requirement. In addition to accessibility and traffic distribution, the architect should also consider about the intersections, traffic lights, private lanes, and potential detours due to occasional road maintenance as well. So moreover, self-driving cars and drones that deliver mail and other inventions might come into the picture in the future as well. So analogous to this, the design of a system on chip also face a similar set of challenges when designing a communication infrastructure for connecting all the cores of a system on chip. So in the early system on chips employed bus and crossbar architectures, traditional bus architecture had dedicated point-to-point connections with one wire dedicated to each signal. When the number of cores in the system on chip is low, the bus are cost effective and simple to implement. But due to the increasing SOC complexity coupled with the increasing number of cores, buses often become performance bottlenecks in complex system on chips. This coupled with other drawbacks such as non-scalability, increased power consumption, non-reusability, variable wire delay, and increased verification costs motivated the researchers to search for an alternative solution. So the inspiration came from the traditional networking solution, more specifically the internet. The network on chip, a miniature version of the wide area network with routers, packets, and links were proposed as the solution. So the new paradigm described a way to communicate in between intellectual property codes, including features such as routing protocols, flow control, switching, arbitration, and buffering. With increased scalability, resources, reuse, performance and reduce costs, design risk, time to market constraint. Network on chip became a solution for the complex system on chips that required scalable interconnection architecture. So now you have an idea about why prefer network on chip communication for system on chips. So basically, a network on chip architecture is widely used to interconnect the intellectual property cores in the system on chip designs, and it is a packet-based communication approach. So as you can see, this is compared with the bus-based Manico architecture. So uh, what's different from a bus-based architecture is that there's an interconnection network in a network on chip, which is used to communicate with the multiple cores in the system on chip. So the network on chip has allowed computer architects to fully utilize the computational power in a system on chip by facilitating low latency and high throughput. So it is considered as an aggressive long-term approach for on-chip communication because it can deal well with the design issues of communication, performance, power consumption, signal integrity, and system scalability. So in terms of the roles of a network on chip, shared memory systems and message passing systems are the two roles that it can do. In shared memory systems, it transports cache lines and cache coherent messages between caches and the memory controllers in a shared memory uh, chip multiprocessor. So in terms of message passing systems, it transfers data between intellectual property blocks in multiprocessor system on chip designs. So this is an example for you guys to get to know about what is a network on chip is. This is an example network on chip interconnection architecture consisting of several processing elements connected together via routers and regular size wires. So now you have an idea about what a network on chip is, what a system on chip is, and what are IP cores. So network on chip interconnection architecture uses a packet-based communication approach, as you all know. A request or a response that goes to a cache or to of chip memory is divided into packets and subsequently to flits and injected to the network. So When a message is coming to the network, it comes as a long message. So the message is divided into packets, and each packet is divided into certain amount of flits. So the flit is the smallest unit of flow control of a network on chip. A packet can consist of one or more flits. For example, assume S is a processor IP core, whereas node D is a connected to an off-chip memory interface, maybe a memory controller. When a load instruction is given and executed as is, it first checks the private cache located in the same node as if it is there's a cache miss or not. So the required data has to be fetched from the memory. Therefore, a memory fetch request is created and sent on the appropriate virtual network to the network interface. The network interface then converts it into network packets according to the packet format, fliticizes the packets and sends the flits into the network via a local router. The network is then responsible to route the flits to the destination, which is D. Flits are routed either along the same path or different path depending on the routing protocol, which we are going to discuss later. The network interface at D creates the packet from the received flit and forward the request to D, which is then initiates the memory fetch request. The response message from the memory that contains the data block follows a similar process. So similarly, all intellectual properties integrated in the system on chip leverage the resources provided by the network on chip to communicate with each other. So this is a small introduction about how communication is happening in network on chip architecture. So this is the breakdown approach of how network on chip traversal is happening. So first, a message is created and injected into the network on chip. Then the created message is converted into network on chip packets and then into flits. And the flits are injected into the network on chip via the local router of the IP core. And then it is the flits are routed from the source to destination, and at the end where it reaches the destination, the flits which are separated into parts from the packet were recreated into the message and sent to the destination. So this is happening through source intellectual property, which is an IP core, as I mentioned, then the network interface, then the routers and the link, and finally the network interface at the destination. And also the image below shows the format of a memory request packet and a response data packet used in the Gem5 architectural simulator, which is the simulator that I'll be using for a demonstration, maybe today or in the next webinar. So this is how a memory request is there. So it it has the destination, requester, message size, cache coherence, request type, and any other headers and the address that is need to be set. So then it's about the topology of a network on chip. So there can be like multiple topologies in network on chip architecture as well. The topology defines the physical organization of intellectual properties, routers, and the links of an interconnect. So this figure shows the mesh topology, which is in the right corner. And there are like crossbar, point-to-point, 3D mesh, a few other commonly used topologies there as well. So the topology is chosen depending on the cost and the performance requirement of a system on chip. The topology directly impacts the communication latency when two intellectual properties are communicating, since it affects the number of links and the routers of fleet has to traverse through to the given destination. A major trade-off when deciding the topology for a given requirement is between the connectivity and the cost. So for an example, if we consider about a ring topology, if we say like there are like 8 components in a ring, the hop count is like 4 for a ring topology, as well as if we consider the same topology for a mesh as well, it has the same hop count, but the average hop count might be different than that as well. So the 2D mesh topology is the most common topology in network on chip designs because each link in a mesh has the same length, leading to ease the design, and the area occupied by the mesh grows linearly with the number of nodes that are involved in the topology. So in most of the designs of network on chip architecture, we can easily find a mesh architecture there. So uh, then it is about how we are routing packets in network on chip as well. The routers comprises of input buffers that are accepted by the packets from the local intellectual property via the network interface or from other routers connected to it. So based on the address in the packet headers and the routing protocol, the crossbar switch routes the data from the input buffers to the appropriate output. So the buffers are allocated for virtual channels, which helps to avoid deadlocks, which can happen in network on chip uh, communication. So I'll be explaining about deadlocks in future webinar. So this like the routing protocols are classified into different architectures. Like one is deterministic routing protocols, the other one is adaptive routing protocols, the other one is oblivious routing algorithms. So in deterministic routing, each packet traversing from the source to destination follows the same path. So XY routing, which is under oblivious routing algorithm, is one of the common example for deterministic routing. In XY routing, packet uses X directional link first before using Y directional link. An example includes these three paths taken by XY routing in a mesh, shown here as well. So adaptive routing takes network states such as congestion, security, reliability into account and takes the fleet through different paths based on the current state of the network. So uh, now you have an idea about what is a system on chip is, what is a network on chip is, and now you know how routing is happening in system on chips using network on chip. So this is a commercial network on chip example. Like there are like many examples of commercial network on chip based system on chip. This is an illustrative example that we can describe about. So this is the about the Intel night landing architecture. So this shows an overview of the Intel night landing architecture together with the network on chip traversal from a memory request. So the architecture implements a directory-based cache coherence protocol and supports two types of memory. One is high bandwidth, low capacity multi-channel uh, DRAM, so we call it MCD RAM as well. So the other one is low bandwidth, high capacity double data rate memory, that is the DDR. These two memory types can be configured in three configurations. One is cache mode, the other one is flat mode, the other one is hybrid mode. These are known as memory modes. Furthermore, the affinity between cores here, cores, directories, memory controllers can be configured in three modes as well. So these are known as all-to-all, quadrant, and subnuma. So which are known as cluster mode. So literally there are like two modes in these memory controllers. One is the cluster mode, the other one is the memory mode. Each combination here of memory and cluster modes are intended to optimize performance based on the application requirement, and they cause different traffic patterns in network on chip as well. So the communication between the nodes are facilitated by the Intel mesh on-die interconnect architecture that is widely deployed in the Intel Xeon processor family. So if you have time to look at the Intel Xeon processor family and know about Intel night landing architecture, you can get an idea about how system on chip is there. So the interconnect consists of four parallel networks, each delivering packets belonging to different types, and each network enforces YX routing protocol here. So in XY routing, it first goes in the X path and then takes the Y path. In YX routing, what happens is like it first follows the Y path and then it goes to the X path. So this example shows that the network on chip traversal of a memory request when the cache memory mode is used and all with the all to all cluster mode. So after a level 2 cache miss, a request is injected on the network on chip in the form of packets to check the tag directory according to the cache coverage protocol. So upon a directory miss, so as I mentioned in earlier when giving you an example about how communication is happening through network on chip, the request is sent to the next element in the memory hierarchy. So that is the MCD RAMs, which is mentioned here. So since the cache mode is used, MCD RAMs acts as the last level cache. The cache miss at the MCD RAM causes a DDR memory access through the DDR memory controller. So when the requested data is retrieved from memory, it is sent back to the original request as well. So therefore, it is evident here like in network on chip, performance is critical to the overall performance of the system on chip because because for an example, the interconnects in Intel night landing architecture is capable of delivering more than 700 gigabits per second of total aggregate bandwidth. So what happened is, if I explain simply, so uh, if you say like this number one processor want to send a message to, yeah, yeah. So if you consider about this processor at number one, which is the above one, want to send a message to the green colored IP core. So what happened is like, so first it checks whether it is already in the buffer. So if it is not already in the buffer, it goes to number, it uses YX routing protocol and it reaches a IP core which is connected to a MCD RAM. So MCD RAM is a memory controller, so it can fetch the data that is required to be sent to um, the one which is mentioned in the green color. So it fetches the data from the MCD RAM. So then it takes that data to the IP core in the green color tile, and then a message is sent to the originator that the message has been delivered. So that's what happens here. So the architecture that is used and the topology that is used in network on chip are critical for this performance because like if we consider about bus based architecture used here like connecting all the IP cores with a single bus, these messages will flood the network and it will be congested. So that's why a solution like network on chip architecture was used here. So then moving on, so this is like the last thing that I'm going to talk about. So this is about the emerging network on chip technologies. So when network on chip was first introduced, the discussion was on the electrical wiring that connects the network on chip together. So this is referred as the electrical now network on chip. So the one that we discussed was the electrical network on chip. However, the recent advancements have demanded exploration of other alternative as well. So with the advancement of manufacturing technologies, computational power of intellectual properties have increased significance, and as a result, the communication between system on chip components have become the bottleneck. So irrespective of the architectural optimizations of electrical network on chip, there are like inherent limitations due to the physical characteristics of the electrical wire that is being used. So therefore, it is becoming like increasingly difficult for an electric network on chip to keep up with the delay, power, bandwidth, reliability, and delay uncertainty requirements of state-of-the-art system on chip architecture. So these challenges can only like intensify in future in giga to tera scale architecture. So what is needed is like a solution is needed to overcome challenges faced in electrical. So in fact, like The International Technology Roadmap for Semiconductors has mentioned optical and wireless based on-chip interconnect innovation is the key to addressing these challenges in the future. So the proposed type of network on chips are wireless network on chips and the optical network on chips. So a wireless network on chips was proposed as a solution to latency experiment experience in electrical nodes, which are based on metal interconnects and multi-hop communication. So wireless network on chip integrates the on-chip antennas and suitable transceivers that enable communication between two intellectual properties without a wide medium. Silicon integrates antennas communicating using the millimeter wave range is shown to be visible technology on chip communication. So if I have to explain what is happening in the wireless network on chip, so if we consider a network on chip, yeah, yeah, if we consider a network on chip in electrical NOC, so if the message is going from J to D, so it has to pass through several nodes as well. Like if the destination is D and the source is J, it has to go through K, L, and H to reach D. But in a wireless network on chip, what happens is like instead of having multiple hops from source to destination, there's like a single hop. So with a single hop, it can go from D to J to D. So the congestions that can happen will be reduced, and they can be like applications that can run in a network on chip can be complex because of the use of electrical network on chip, because like we'll be like limited to a set of applications that are running and using some parts there. But when it comes to wireless network on chip, it can be reduced because there's a single hop instead of multiple hops. So the other solution is like uh, uh, optical network on chips, also known as like photonic network on chips. So this use photo emitters, optical wave guides, and transceivers for communication. The major advantage over electrical network on chip is that it is like possible to physically intersect light beams with minimal crosstalk. So this enables simplified routing, and together with all the properties, optical network on chip can achieve bandwidths in the range of gigabits per second. So uh, as you can see, when compared with the electrical network on chips, in wireless network on chips and optical network on chips, the bandwidth can be increased without an issue. So we all know that as we discussed in the previous webinar, the number of cores in an integrated circuit is increasing in the past few years, like from tens to hundreds and maybe thousands in the future as well. So the system on chip is getting complex day by day, and the communication architecture should have a bandwidth to communicate with all those IP cores inside of a system on chip. So as a solution from the electrical network on chip was the solution, but from the electrical network on chip, uh, we have to increase the bandwidth, and for that we use wireless network on chips and optical network on chips. So the bandwidth issue is reduced there. So then there's a problem like when we are going to wireless network on chips and optical network on chips. So the message passing will be completely different, and we have to think about the security aspect. So I'll be talking about the security about this in the next lecture. So just to give an overview about what I discussed here today. So there might be like lots of new terms that have came across you all. So you don't have to worry. Like what you have to get is like there are like several different models in network concept. Like there are different topologies, and that's all you have to know about this, because in the next webinar we are going to talk about the security. So just to give you all a recap about what I discussed today. So now you have an idea about how the communication is happening through network on chip, as I discussed, compared to a road network. And as I explained, like now how communication is happening on network on chip, now you can have a clear idea like an architecture like bus architecture or point-to-point architecture cannot be used here. So now you know that complex architecture such as network on chip is needed. Then I think now you are able to understand this image that is mentioned here. Like this has like different IP cores connected to each other, and in the middle you can see the network on chip architecture. So now you, when you see this image, now you have an idea like how the messages are passing from maybe from the memory to the FPGA or from the memory to processor. So now we have an idea about how it is passing. And I've talked today about the network interfaces and the routers as well. So it is simple, like if I am to explain about it again as well. So what's happening here is communication. So the communication is like we want to pass a message. So when we are passing a message, what happens is like we get the message from the core, and then the message is converted into packets. So this conversion happens in the network interface. So it is converted into packets, and those packets are then divided into plates. So those things are happening in the network interface, and then it is fed into the router. So if there was a confusion, you can now I think it was explained well. So this is like if we want to like explore about what happens within a router, like how a router is how a router is thinking, like where it should like send the message, what is the next router, and how the communication is happening. So if you are like interested in this area, like you can look into what are input buffers, what are VC allocators, what are switch allocators, and what are crossbar switches. So this is like pretty much similar to the network architecture in internet as well, but only difference is like this is on chip. This is about on chip communication. So if you want to get a simple idea about how communication is happening, this image will clarify your doubt. So that's it. And I think like now you know that there are like different topologies. That means the ways that we can communicate with it, the paths that we can have to communicate with the IP cores are there. So these are three type of topologies, and I think like now you know what is a mesh topology is. So there's like XY routing is used in network on chip architecture, and in XY routing as well. This is not like the ultimate solution to on chip communication. The way that we have to do communicate with there. So there are like XY routing, XXY routing, and there are like YX routing, YYX routing, and there are like several kind of routing algorithms, and you can have a look about that as well. So I think like if you are familiar with what is Manhattan distance and the uh, other algorithms that are used in communication, so this is an interesting problem to you to explore as well. So this is as I described earlier. This is the Intel night landing architecture that is used as commercial network on chip based system on chip. So this gives you the complete idea about how this is being deployed and what are there. So at the end, I think like now you have an idea about what a network on chip is and what a system on chip is like. So system on chip is like, again, if I have to summarize it, it's a single integrated circuit which is implemented in a single silicon die. And when we have like one or two components inside the single silicon die, we can easily uh, communicate with them maybe via bus-based architecture or point-to-point architecture. But when the number of components inside this single silicon die increases, what we need is a complex communication architecture to communicate on the chip. So for that, we came up for that. This researchers have came up with network on chip by considering about how it was deployed in the internet. So this is currently we are like exploring about what are the possible things in electrical network concept, about how a network concept can be validated and how a network concept can be verified, or what are the security vulnerabilities in an electrical network concept, how can we overcome them. And that's what currently happening in electrical network concept. And then there are like issues in the electrical network concept, like uh, we have to like go through several, we have to go through a path to reach the destination in electrical network concept, mainly because we are using a wiring to send messages in the electrical network concept. But the wiring is the only thing in the electrical network concept that is a problem for the bandwidth of the communication. And to overcome the bandwidth of the communication, instead of wiring, wireless architectures are considered, like they are wireless network concept and the optical network concept. So the future of network concept is about wireless network concept and the optical network concepts. And if you're interested, you can explore about that as well. So I think like I have covered what I wanted to cover today. So now you have an idea about what a network concept is and what a system on chip is as well. So in the next webinar, maybe like I'll be able to give you a demonstration about how communication is happening in a network concept using Garnet 2 system synthetic traffic generator. So like that's pretty much it from today. So thank you very much. If you have any questions, please let me know so I'll be able to answer. Thank you. Hello. Hello, can you hear me?
Yeah.